This is the second video of the related rates problems. In these examples, you are going to have to start with drawing yourself a sketch before you are able to start solving the problem here. And we're going to follow the same kind of method that we did last time, is we're going to kind of write down what all we're given, and we are going to write down what we're going to find, and we're going to write down the equation that ties our variables together. So here's some kind of hints up above. If the problem mentions area, you're most likely going to use an area formula. If it mentions volume, you'll most likely use volume. If it mentions length of sides and figure is a triangle, you'll probably use Pythagorean theorem. And if it uses angle measures, you'll probably be using trigonometric ratios. Okay, this one's really important. This step 4 is make sure you never plug in a constant before you take the derivative. You have to take the derivative first before you plug in all the information that you know. Step 5, make sure you differentiate with respect to time. Everything is taking a derivative with respect to time. And then just make sure at the very end you've actually answered what the question is asking. So we're going to start out with your example 5. We got an oil tanker spill. An oil tanker spills oil that spreads in a circular pattern whose radius increases at the rate of 50 feet per minute. How fast are both the circumference and area of the spill increasing when the radius of the spill is 20 feet and 50 feet? Okay, both of these are going to basically be the same, except I'm going to just do one of them. So we'll just do the 20 feet one. Okay, so I want you guys to start out, draw yourself a picture of what you think this would look like, and try labeling the information that you would know. When you've done that, go ahead and unpause the video and check to make sure that you have what I have. So hopefully draw yourself a circle. It is obviously going to increase outwards in a circular pattern, so it's only going to continue to get bigger. We know that the rate at which it is increasing is 50 feet per minute. It's asking us back at the beginning, or at the end of the question, it's asking us to find how the circumference and area are increasing. So we're actually going to find dA dt and dC dt, specifically when our radius is 20 feet. So in this case, is there a formula that relates area and circumference and radius all together? No, so we are going to have to use two different equations. So our first equation for area is area of a circle, pi r squared. Circumference of a circle would be 2 pi r. So we're going to have to do these individually in order to figure out how fast the circumference is increasing and how fast the area is increasing. So let's go ahead and take the derivative of my area. So dA dt is equal to 2 pi r times dr dt. So I can go ahead and plug all that information in that I know. dA dt is equal to 2 pi times 20 feet times 50 feet per minute. And when there's a pi, we're going to leave our answer in terms of pi. So our area is increasing at a rate of, if I multiply all this together, is 2,000 pi feet squared per minute. And that makes sense that area should be squared, and it's a rate, so it should be per time, in this case per minute. So what this means is that our oil spill, the area of the oil spill, is increasing at a rate of 2,000 pi square feet per minute. Now we got to figure out our circumference. So let's take the derivative of our circumference formula. So dC over dt is equal to 2 pi dr dt. Plug in the information we know. I've got 2 pi times 50 feet per minute. So our circumference is increasing at a rate of 100 pi feet per minute. And circumference is not going to be squared, so this feet per minute does make sense. It's saying that our circumference of the oil spill is increasing at a rate of 100 pi feet per minute. Okay, let's look at the next example here. Got a falling ladder. Okay, we've got this 13-foot ladder that leans against a vertical wall. If the lower end of the ladder is pulled away at a rate of 2 feet per second, how fast is the top of the ladder coming down the wall at the instant the top of the ladder is 12 feet above the ground and at 5 feet above the ground? So the hardest part of these problems is drawing the picture. So go ahead and pause this video, draw the picture of what this scenario means, and then unpause the video to check to see if your picture matches mine. Okay, so here's what your picture should somewhat look like. Our ladder is 12 feet tall. I'm going to label this X. I'm not sure what this distance is. I'm going to label this Y. Not sure what that distance is yet. And then we know that we are changing at a rate of 2 feet per second is when this ladder is kind of being pulled out that way. Okay, so going back to that question here, it's asking us how fast is the top of the ladder coming down the wall? So that means we're looking over here at how fast is this coming down. So we're trying to find my dy dx, specifically when the top of that ladder is now at 12 feet. Oh, I made a mistake. This should be 13. Okay, so specifically when your y value is equal to 12 feet. So how does the relation of sides work in a triangle, right? We've got x squared plus y squared is equal to our hypotenuse squared. So our equation that we're going to use is Pythagorean theorem because we're not given anything about angles. We're just given side lengths. So I've got x squared plus y squared is equal to 13 squared. And I can go ahead and take the derivative of this with respect to time. So I'm going to have 2x dx dt plus 2y dy dt is equal to 0. So now I can plug in the information that I know. I don't know what x is, but I do know what dx dt is. That would be 2 feet per second. And then I do know my y. My y value is 12 in this case, so times 12 feet. But then I don't know what dy dx is. Or sorry, dy dt. And this all equals 0. However, I did make one slight mistake because I've got two variables. So let's kind of go back here, look at our picture. Which variable can I solve for still? Can I solve for x or can I solve for dy dt? Well, I do know that this height now is 12 and my ladder is at 13 still, and I know my side length of x. So I have this triangle here. So I can figure out what x equals with my Pythagorean theorem. So this is actually another Pythagorean triple, so this would be 5 feet. Let's go ahead and plug that in as well. So I've got 2 times 5 feet. So if I simplify this, I'm going to end up with 2 times 5 times 2, which would be 20 feet squared per second, plus 24 feet times my dy dt. And I want to get the dy dt by itself, so I'm going to subtract that 20 feet squared. And then I have to get rid of the 24 feet, so divide by 24 feet. And I'm left with dy dt is equal to, I can simplify this fraction, divide both of them by 4, so I got negative 5 over 6. Now my feet unit is going to cancel out one time with the top one, so I'm going to be left with feet per second. Okay, so what does this mean in terms of the problem? If I go back up here, the original question was asking us how fast is the top of the ladder coming down the wall when it is at 12 feet above the ground. So it is going down at a rate, it is decreasing, right, at a rate of 5/6 feet per second. So it's getting closer to the ground at a rate of 5/6 feet per per second. Okay, if I did letter B, it'd basically be the same thing, so I'm going to just cross that one out, and we're going to move on to the next problem. All right, next example here is about a camera. We did do letter B already, so you should already have your picture drawn for letter A as well. It's using the same picture, it just knows some different things. So I'm going to go ahead and draw the picture on here and show my work for this problem. It's again going to be using Pythagorean theorem, so very similar to the one that we just did. So look through it, try it out, pause this video, and then unpause it to see what the answer is. So hopefully you pause this video, tried it out yourself. You should end up getting 640 feet per second. So that distance between the camera and the rocket is changing at a rate of 640 feet per second. You did have to do another little Pythagorean theorem triangle over here, but it was another nice Pythagorean triple. So it was a 3, 4, 5 triangle, just a multiple of that. You should already have letter B finished on this one. If you don't, go ahead and check yours with a number, or letter B was using trigonometry. All right, we're going to go ahead and skip example 8 and move on to example 9, where we have some similar triangles that we have to talk about. All right, 2 more examples here. We've got example 9 about a draining tank of water. So we've got water draining from a conical tank with the vertex down at a rate of 2 meters cubed per second. The tank is 16 meters high and its radius at the top is 4 meters. How fast is the water level falling when the level of the water is 12 meters high and when it is 2 meters high? Again, we're just going to do one of these because it's going to be the same process. So we will just do letter A. But go ahead and pause this video, draw a picture of what you think this looks like, and label all of your given and what are we trying to find. So hopefully your picture looks something like mine. We've got a cone, the height is 16, radius at the top is 4, but we're looking at when is the height going to be 12? What is the rate? How fast is the water going to be falling when that height is 12? So we are trying to find dH dt when our h is equal to 12 meters. So the equation that we're going to use, if you aren't sure about what the equation of a cone is, you can look it up if you need to. Otherwise, your equation is 1/3 pi r squared times h. So if I were to take the derivative of this right now, I would have too many unknowns. I wouldn't know what my r value would be of this little red triangle down here. I don't know what my dr dt would be, and I don't know what my dH dt is. So when you have a problem like this, you're going to have 2 similar triangles to look at. So I've got a bigger triangle here of the 4 and the 16. But that triangle is going to be similar to that smaller triangle there in red of 12 to r. So we don't know what r is, but we can go ahead and set up, oh, my bad, we aren't plugging in values until the very end, so can't plug that in yet. So I'm going to say that's h still. So let's go ahead and solve for r in terms of h. So similar triangles. You can kind of set these up a few different ways. I like to go corresponding side to the corresponding side on the other triangle. So if I start with side length of 4, that should be similar to the side length of r. So I'm going to write that as a proportion. 4 over r, and that's going to be equal to, since I started with that big triangle, I have to start with that big triangle on my second one. I've got 16 to h. So it'd be 16 over h. Now if I cross multiply this here and solve for r, I'm going to have 16r is equal to 4h. Divide by 16. And I get that r is equal to h over 4. And I solved for r because we're trying to find dH dt, and I know what h is equal to, so I'm going to be able to plug this value into my equation and then only have the variable of h left over. So we're going to take this now and plug this in here. So my equation that I have now is 1/3 pi times h over 4 squared times h. So let's simplify that before I take the derivative. So I've got 1/3 pi times h cubed over 16. I can simplify one more time, take that fraction out in front. So I've got 1/48 pi times h cubed. So now I need to take the derivative of this. So derivative of this volume, so dv dt, is equal to, this is just a constant, so I'm going to leave that out front. So 1/48 pi, and then take the derivative of h cubed. That would be times 3h squared dh dt. Now I can go ahead and plug in my h value. My h value was 12. Okay, be careful there. Your only thing that's actually squared is your h. I almost fell into the trap of timesing 3 and 12 together before I squared it, but it is just the h that is squared. I also forgot we know what dv dt is. dv dt is actually -2 meters cubed per second. I forgot my units here for 12 meters as well. So now if I plug everything in on the right-hand side of my equation into my calculator, except for the pi, I'm going to end up with 9 meters or 9 pi meters squared times dh dt. And now we can divide that out. And my units are going to cancel 2 of those meters squareds out. So I'm going to be left with -2/9 pi meters per second. So that water level in that cone is falling at a rate of -2/9 pi meters per second. Okay, me and my shadow, last example. We've got a 6-foot tall person is 12 feet away from an 18-foot tall lamppost. If the person is moving away at a rate of 2 feet per second, what rate is the length of the shadow changing? And at what rate is the tip of the shadow changing? So go ahead and pause this video, try drawing yourself a picture, and then unpause it to see if your picture matches mine. Okay, hopefully your picture looks somewhat similar to this. The only part that I'm making some assumptions where we made mistakes was at this labeling for your rate down here below. So in this picture here, we've got 2 similar triangles. I've got this larger triangle and this smaller triangle. Now, I know I'm going to have to use something with similar triangles because I don't know anything about my hypotenuse, so I can't use Pythagorean theorem, and I don't know anything about my angle, so I can't use trig. So we are trying to find what is the rate of this changing? What is the rate of the shadow changing? Think about if you have a light post, right? The shadow is going to be in front of you over here. So how is this changing if you're moving at a rate of 2 feet per second this way? So I'm going to draw these 2 larger triangles out down here. So I've got 18, and then we're going to label this D plus X. And then I've got my smaller triangle with the man of 6 feet and a side length of X. So my equation that I'm going to use is proportions of similar triangles. So I'm going to start with that short side there. So 18 over 6 will be on one side of my equation. And then I will have D plus X over X. And now, instead of taking the derivative and using our quotient rule, I would just go ahead and simplify this before we actually start taking the derivative. So I'm going to go ahead and cross multiply here, and I get 18x is equal to 6d plus 6x. I can move that 6x over to get 12x is equal to 6d. So now I can go ahead and take the derivative of this. So the derivative of this would be 12 times dx dt is equal to 6 times dd dt. And I know what dt is, so I can plug that value in. And then if I simplify this, I get dx dt is equal to 12 feet per second. Oh, but I forgot that 12 over there. So the 12s are going to go away. So my rate at which this is changing is just 1 foot per second. So that length of the shadow is growing. This piece right here is growing at a rate of 1 foot per second. Part B asks us what rate is the tip of the shadow changing. So the tip of the shadow does not just rely on the dx dt, but it relies on this whole thing of dd dt and dx dt. So if I wanted to find what the rate is of both of those things, I would just add those together. So I want to find what is dx dt plus dd dt. If I add those two things together, I have 1 foot per second squared plus 2 feet per second squared to give me 3 feet per second. Not squared. I said squared. It's not squared. Just 3 feet per second. Okay. So that's kind of one of those other examples of making sure you're answering the question, because, you know, on an AP test, they might just ask you the second question and not ask you that first question. So make sure you are looking back to see that you are answering the full question. If you listen to this whole video, go ahead and send me your favorite part of Thanksgiving break, and I'll give you some extra credit on a quiz. Thanks. Have a great day.